Let's talk about solutions of phase diagram problems. So what we'll do now is usually we have a couple of measurements. Maybe we know the total volume and the water content. We can assume a specific gravity. And we want to solve for some things like the dry density and the saturated density and the void ratio or something like that. So basically what we want to do first is solve for all of the individual masses and volumes that are associated with the phase diagram. So if I come back up here in my notes, once we know the values for all of these quantities, then we're good. We can calculate any density, any void ratio, anything we want to do. So the goal you should have in mind when you're starting out with phase diagrams is to fully populate all of these masses and volumes. Once you have that, super easy to apply our definitions and just calculate everything out. Eventually, once you get familiar enough with phase diagrams, there are some shortcuts that you might memorize, and you can just jump straight to the end. You know, if you know the water content, the specific gravity of solids, you know, for example, maybe you can just directly calculate the saturated unit weight. Okay, but first, let's just talk about solutions to solve them that are not shortcuts, because one thing that tends to happen is students often want to just jump to the end and do the shortcuts right away. I've been through this class enough times to realize that students will make mistakes when they do it that way. So I really do recommend that you take your time with these and actually compute all of the masses and volumes first. It doesn't take that long. It's not that cumbersome, so it's not a big deal. So the most important first step that you should always start with is to draw a phase diagram. You want to actually have a drawing with all of the different masses and volumes labeled, and leave enough space so that you can write numbers in there too, because you're going to want to add the numbers so that at the end you can go through and quickly compute the things that you want. So you want to show all of the known quantities and the unknowns, right? So label everything you know, leave everything else blank, and then solve for the desired quantities. It's really basic. I mean, this is not difficult math or anything like that, so no problems. You just have to be a little organized in your approach. So the steps you should follow: first, list all of the things you know. Okay, maybe you know the water content and the total unit weight, and you can assume a specific gravity. You know, make sure you acknowledge anything you're assuming, any assumptions you're making, and you want to make sure that you have enough information to actually solve the problem. So we'll talk about that in just a second. Step 2, draw the phase diagram, fill in the knowns and unknowns. Just draw the actual stack of solids, water, air, put volumes on the left, masses on the right, and fill in the things that you know, leave the other ones blank. The third one's really important. Try to avoid big formulas. These things actually are really simple. If you're deriving formulas that are complicated, you're probably doing extra work that you don't need to do. Maybe that's a good time to step back and think about it a little bit more clearly and try to make really simple and straightforward formulas. There's not a lot of algebra required here. So if you're doing a lot of algebra, you're probably going down the wrong path. So that's a good thing to keep in mind. All right, now an important one. Sometimes we're not given masses or volumes. So there's two different kinds of phase diagrams. One would be for a very specific amount of soil. Like, let's say you have a sample. It's in a tube, you push the tube into the ground, and you have a sample that's in a cylinder, and you know its height and you know its diameter. In that case, you have a fixed volume and fixed mass, and you can move forward with the phase diagram calculations for that sample, right? So maybe it weighs 500 grams or something like that. So that one is probably easier for us to conceptualize because it's an actual thing that we're calculating. Okay, but then there's the soil that's in the field from which you took the sample. We're assuming the sample's representative of what's out there in the field. We don't want to go and compute the whole volume of all of that soil in the field beneath the building and weigh it or something like that, right? So what we're going to do is measure the phase diagram for this known mass of soil, but we're going to assume that the phase diagram for the soil out in the field, where we don't have a fixed mass or volume, is actually just the same, right? The water content's the same, void ratio is the same, all that stuff. So you could think of it like two different kinds of phase diagrams, one for an actual fixed amount of soil, and one that's just kind of for the soil in general. And it's the second kind that we're actually going to do more frequently, and that's the example that I'll do here. Although I think when we do discussion in class, I'll start you with one that is for a fixed amount because it's a little bit easier to do. So if no masses or volumes are given, if you're solving for just kind of like this undefined amount of soil, what you can do is assume 1. You can set something to be equal to 1, or whatever number you want, but there are strategies that make this easier. Usually we'll set the volume of solids to be equal to 1 meter cubed, for example, and then we'll solve for the other volumes based on measured water contents and stuff like that. Okay, then step 5, you'll start filling in one side, either the volume side or the mass side, until you get stuck and you can't move further with the phase diagram because you don't have enough information. Once you get stuck and you can't move forward, you need to cross over to the other side, right here, cross over to the other side, and the way we do that is using mass density. So you want to go from, let's say you know the volume of solids, but you don't know the volume of water or the volume of air. Well, now you can cross over, and knowing the density of solids, you can compute the mass of solids. And so this is a common thing, right? Maybe we'll know the volume of solids, we compute the mass of solids, then we know the water content, so we're going to compute the mass of water. Now we have 1 volume and 2 masses. We can move back to the other side using the mass density of water and then fill out the volume of air, and we're done. So it's important to remember how you can cross back and forth. Then I usually do all of this in symbol form and then place the numerical value with units in the same order and solve them. And then check your units at the end and check the reasonableness of your answer. If you calculate that the total mass density of the soil is higher than steel or something like that, that's not reasonable. Okay? There's no way that the total density can be higher than the density of the solids, right? Because the water and air are less dense than the solids. So a lot of the time it's a unit issue. You've done kilograms instead of megagrams or something like that. So just do kind of a check at the end, make sure your answer is reasonable. If it's not, go back and figure out where the mistake was. So let's do an example problem. We're given a soil and we know that the total density is 1.76 megagrams per meter cubed. Right, so that's a reasonable number. I mean, water is 1 megagram per meter cubed. The solid particles themselves are usually about 2.7. We're going to assume that the density of solids is 2.7 megagrams per meter cubed. So the total density is in between the density of water and the density of solids. Totally makes sense. And then we have the water content as 10%. All right, so we might get these measurements from the field. You know, maybe there are different ways of measuring total density. The simplest way is to take a known volume of soil, measure its mass, and you got the total density. There are also other methods that use, like the nuclear gauge. It sends out radiation, and you can get water content and total density that way. So anyway, it's fairly common to have this particular set of information. And then we want to compute the dry density, void ratio, porosity, degree of saturation, and saturated density, right? So compute a lot of different things here. And what you'll notice is that we have densities and we have water contents. We don't have any masses or any volumes specified. So this is one of those classes of problems where we don't have a fixed volume or fixed mass of soil we're working with. We're just talking about the soil overall as a whole. So what we're going to do is draw the phase diagram. Here it is, solid, water, air. Then we have all the volumes. I didn't put in the volume of voids. I probably should have a line there for that. Right, there's this one right there would be volume of voids. Then we have the masses on the right side, mass of water and solid in total. Okay, now let's go through our steps here. We've done number 1, right? We've listed the givens, so we know what we know. And we've drawn the phase diagrams. And we've filled in the knowns and unknowns. We actually don't know any of these volumes or masses to start out with. So we're done with steps 1 and 2. Okay, then we'll move on to step 4 right here. if no masses or volumes are given, you can assume either one volume or one mass, right? So you can't assume more than one thing, but you can make one assumption, and basically you're saying, I'm going to solve it for this overall mass of soil, but I'm going to do it just for a fixed volume, right? So let's see, the assumption that I make here is that the total volume is equal to 1. I would recommend actually doing the volume of solids. That usually makes the algebra a little bit easier, but it's not difficult anyway. So we're going to set total volume equals 1 meter cubed. Okay, so now we're going to use the definition of water content, right? The water content is 10%, which is 0.1. That's equal to the mass of water divided by the mass of solids. So we know that the mass of water is 0.1 times ms. We also know the total density. Rho is equal to mt over vt, which is mw plus ms over vt. Okay, and now we can put in our water content definition right there, and we know that rho is equal to 1.1 times the mass of solids divided by the total volume. So we know the total volume, right? We just set that to be 1 meter cubed. And we know the total density, so now we can solve for the mass of solids. We've got a determinate equation. So the mass of solids is rho Vt over 1.1, and you get 1.76 megagrams per meter cubed times 1 meter cubed divided by 1.1, and you get the total mass is 1.6 megagrams, mass of solids. So now if we go up here, we can write in, what was it? 1.6 megagrams here, right? I didn't really leave enough space. I think I have another one down here, yeah. Okay, so down here I've written in the mass of solids is 1.6 megagrams, so we're starting to fill out our phase diagram. Then we know water content, so it's easy for us to compute mass of water, simply equal to the water content times the mass of solids, right? And so we get 0.16 megagrams. So 1.6 here, 0.16 megagrams there, and then we know the total mass is 1.76 megagrams. So we've completed the mass side. Okay, notice that we started over here on the volume side, and then we invoked our definition of total density in order to get these mass quantities. So we've gone from here over to here. Now we have to kind of come back to get these individual volumes of solids, water, and then air by subtracting from the total volume. So what we'll do now is solve for the volume of water. We know the density of water is equal to the mass of water divided by the volume of water. Therefore, VW is MW over rho W, and you get 0.16 meters cubed. Right? Pretty easy to do that one. Then the density of solids is the mass of solids over the volume of solids, and that's equal to 1.6 megagrams divided by 2.7 megagrams per meter cubed, because remember the solids were 2.7 times denser than the water. So you get 0.593 cubic meters of solids. Okay, so we have now added those things to our phase diagram. We have the volume of solids, the volume of water. Okay, and then we know that the total volume was 1 megagram, or 1 meter cubed. So you get the total volume is equal to the 3 component volumes, the air, water, and solids. Well, the only thing we don't know in this equation is the volume of air, so it's easy to solve for it, and you get 0.247 cubic meters of air. So now we have 0.247. I put the units up here, which is perfectly fine. You don't need to include units on every number. It can make the chart a little bit easier to read that way. And then I've also done here the volume of voids. Right, the volume of voids is just equal to, I don't think I have it written out. Let me write that out here. Volume of voids is equal to the volume of air plus the volume of water, which is going to be equal to, whoops, let's see, 0.247 meters cubed plus 0.16 meters cubed. So you get the volume of voids is equal to 0.407 cubic meters, right? So now we have the fully populated phase diagram over here. And at this point, the problem is basically solved, right? We've done the sort of the hard work. All we have to do now is invoke our definitions of void ratio, total saturated density, porosity, and so forth. So that's what we're doing here, right? The dry density is the mass of solids divided by the total volume. You get 1.6 megagrams divided by 1 meter cubed. It's just 1.6 megagrams per meter cubed. Pretty easy. Now that should be lower than the total density, right? The total density that we found was 1.76 megagrams per meter cubed. The dry density should be lower because now we're assuming that we're taking out the mass of water, and it is indeed 1.6 megagrams per meter cubed. So that's the kind of reasonableness check that you should be doing. Make sure that you're getting reasonable numbers. Okay, and then you get void ratio is volume of voids divided by volume of solids, and you get 0.686. Pretty reasonable void ratio. Porosity is volume of voids divided by total volume. You can plug these things in, you get 40.7%. Right? So what that means is that by volume, 40.7% of the soil is open space that can either be filled with air or water, whereas what would be 59.3% of the volume is filled with solid particles. So that's how to interpret porosity. Then degree of saturation is the volume of water divided by the volume of voids, and you get these equations here just by plugging everything in, and you get 39.3% degree of saturation. It's pretty reasonable. Okay, if you get something that's lower than 0 or bigger than 100%, you've got a mistake, right? So it has to be between those two. All right, and then the saturated unit weight. Let's see. I'm not following the equation that I just derived in the last lecture here, but I am computing the mass of water if we replace the air with water instead, right? So in a way, I'm kind of doing the same thing, just a different way. So the mass of water, if the soil was 100% saturated, would be equal to the density of water times the volume of air plus the volume of water. And so you end up with this equation here, and the mass of water would be 0.407 megagrams. So then the saturated density is equal to that mass of water, if it was saturated, plus the mass of solids divided by the total volume, and you get 2.01 megagrams per meter cubed. Turns out that saturated density for sandy soils is usually between 19 and 21 megagrams per meter cubed. It doesn't vary over a huge range. It would be between 19 and 21 kilonewtons per meter cubed, which would be roughly 1.9 to 2.1 megagrams per meter cubed. All right, so that's the end of the example. We've calculated everything that we needed. After we got the phase diagram, all these calculations were easy. So let's talk a little bit about the assumptions that we can make, right? In this example, we assumed that the total volume was 1 cubic meter. I would recommend doing a different assumption, that the volume of solids is 1 cubic meter instead. You'll get the same solutions in the end. Your phase diagram will have different numbers, but all the ratios will be the same. So void ratio, degree of saturation, all that stuff will stay the same. So here we've got it, if you put 1 right there, what that allows you to do is just go directly to the mass of solids, right? When we did the total volume, we had to do a little bit of algebra to get the mass of solids out by invoking water content. If you set this equal to 1, you can just go straight there because you already know the density of solids. Then you can use water content to get right there. Then you can go back here to get the volume of water. Very simple. It's a little simpler than what I did before. I did it this way because it's following the example that's in the textbook. But I did just want to point out that this method is actually a little bit easier, and it's probably the way that I would recommend doing it. All right, the last thing that we'll talk about here is the difference between unit weight and mass density. So what we've been doing so far is solving everything in terms of mass density in megagrams per meter cubed. Sometimes it's done as kilograms per meter cubed, so the numbers would be 1,000 times bigger than what we're showing. But a lot of the time what we want is unit weight instead, right? Since we're all working on Earth, we can assume that the acceleration of gravity is 9.81 meters per second squared. If you were to go and start doing geotechnical engineering on the moon, you would want mass density, right? Because you'd have to multiply by a different acceleration of gravity, or Mars, or whatever. But we can just assume that the acceleration of gravity is constant for work on Earth, so it's not a big deal. So the unit weight is equal to the total weight divided by the total volume, instead of the total mass divided by total volume. And similar for the solid unit weight and the water unit weight. So to convert, all we do is multiply by the acceleration of gravity. And one thing that's really convenient is if you do your masses in units of megagrams per meter cubed, and you multiply by 9.81 meters per second squared, what you get out is 9.81, this is the unit weight of water, 9.81 megagrams meter per second squared per cubic meter. And then if you do some manipulations, you can show that it's actually equal to 9.81 kilonewtons per meter cubed. So in going, that's something you can derive by doing the units, but just recognize that if you have megagrams per meter cubed, multiply by 9.81, you get kilonewtons per meter cubed, right? So it's an easy thing to do. Okay, that's it for this lecture.